In 1896, Henry Becquerel was doing experiments with a sample of uranium salt which he thought might show phosphorescent properties after being exposed to the sun. However, it was cloudy on the days he wanted to repeat the experiment, and the equipment was stored away. Nevertheless, the photographic plates showed signs of exposure, even though they had been wrapped in black, thick paper. He would conclude that the uranium did not need the exposure to the sun to shed those energetic rays that reached the photographic plates. Marie Curie decided to study those invisible rays for her doctoral thesis. She called the phenomenon radioactivity and discovered that other elements such as thorium were also radioactive. 3 years later, Ernest Rutherford experimented with different electric and magnetic environments and identified 3 different types of radiation. He named them alpha, beta, and gamma rays based on their penetrating power and the sign of their electric charge. Let us start with the alpha rays. Before they were identified, alpha rays were known to be less penetrating than the other 2 types of radiation, and when made to travel between the poles of a magnet, they were deflected in a way indicative that they were charged positively. In 1907, Ernest Rutherford let an electric current go through an evacuated glass chamber that had caught some alpha particles, analyzed the light shed, and found that the light composition matched the unique pattern characteristic of the helium element. Later, Rutherford and Geiger established that the electric charge of one alpha particle was 2 elementary charges. Along with his new model of the atom, Rutherford proposed that the alpha particle was an atom of helium without its 2 electrons, so leaving only the nucleus of the helium atom. The fast-moving alpha particle was created from the splitting of the nucleus of an unstable nucleus. The process is called alpha decay. Typically, we start with an unstable nucleus called the parent nucleus. The P used here is not referring to phosphorus, but to an undefined parent nucleus. This parent nucleus then splits and ejects an alpha particle, leaving behind a daughter nucleus. If these are to be the only products of an alpha decay, then the electric charge must be conserved. This is why the daughter nucleus has 2 less protons than the parent nucleus. The conservation of the number of nucleon, which is, if you recall, a special case of the conservation of the baryon numbers, must also occur. Here it means that the number of nucleons of the daughter nucleus is 4 nucleons less than that of the parent nucleus. Here is an example of an alpha decay which Becquerel would have witnessed in his first experiment: uranium changing into thorium. Let us move to the beta rays. Compared to the alpha rays, they were harder to stop. Thin metal plates could block the alpha rays from a radioactive sample, but the beta rays and the gamma rays could still go through. However, the gamma rays were not deflected when passing between poles of a magnet, but the beta rays were deflected in the opposite direction to that of the deflection direction of the alpha particles. The beta particles were then declared to be negatively charged, while the gamma rays had no electric charge. Rutherford found that his beta particles behaved like the fairly newly discovered corpuscles identified by J.J. Thomson in 1897, and which would later be called electrons. The decay of a nucleus that produces an electron will eventually be called a beta-negative decay. I will explain the negative in the name later. A beta-negative decay also starts with an unstable parent nucleus and leads to the production of a fast-moving electron. If only the conservation of charge and the conservation of the number of nucleons were applied, the daughter nucleus would look like this. Notice that the daughter nucleus has the same number of nucleons as the parent nucleus, but it has one more proton than its parent. The beta-negative decay involves the transformation of a neutron into a proton. Further experiments showed that this nuclear reaction did not conserve energy, among other things. So the production of an hard-to-detect particle was suggested and was finally detected experimentally in 1956. It was named the electron antineutrino. It is not a baryon and it has no charge, so it does not affect the conservation of charge and the conservation of the number of nucleons. Here is an example of a beta-negative decay. It is what happens to the thorium nucleus that is formed when the uranium-238 nucleus of the previous example goes through an alpha decay. It can be followed by a beta-negative decay of thorium-234 into protactinium-234. I will explain the meaning of this star later. When Rutherford suggested his 3 different types of radiation, the decay producing a positron had not been discovered yet. It was accomplished in 1934 by Irène Joliot-Curie and her husband when they bombarded a stable aluminum sheet with alpha particles and discovered a new type of radiation once the alpha particle source was removed. This radiation consisted of particles that were positively charged and were just as light as electrons. Irène and Frédéric Joliot-Curie had experimentally created the antiparticle of the electron, very often called the positron, and got the 1935 Nobel Prize in Chemistry for their discovery of artificial radioactivity. The decay that leads to the production of a positron in that fashion has been named beta-positive decay. So the beta-positive decay starts with an unstable parent nucleus and produces a positron. The daughter nucleus that would conserve the electric charge and the number of nucleons would look like this. Notice that just like with the beta-negative decay, the daughter nucleus has the same number of nucleons as the parent nucleus. However, the daughter nucleus has one less proton compared to the parent nucleus. Conservation of energy requires another particle that has the property of the antiparticle of the electron antineutrino, so an electron neutrino. For an example, I will use the beta-positive decay that occurred during the Joliot-Curie experiment. The interaction of an aluminum nucleus with an alpha particle led to the formation of an unstable phosphorus-30 nucleus. This is our parent nucleus here for the beta-positive decay. This time the P really means phosphorus, not parent. The positron and the electron neutrino are produced leaving behind a silicon-30 nucleus. In the periodic table, silicon is the element between aluminum and phosphorus. Now it only leaves us to deal with the gamma rays. Recall that those were seen as not deviating between poles of a magnet and were the most penetrating of the 3 types of radiation. Let us go over the steps in their identification. First, Einstein proposed that the energy transported by electromagnetic waves comes in particle-like packets. These packets will eventually be named photons.
6 years later, Rutherford proposed a model of the atom with a heavy, small nucleus with orbiting electrons. The problem with that model is that the atom should have been unstable because the accelerated electrons should lose energy in the form of electromagnetic radiation and crash onto the nucleus. To counter that problem, Niels Bohr suggested that stable orbits existed only under certain conditions, which meant that only some specific energy values were possible for the electrons. An electron could lose energy only if the photon it emitted had energy exactly equal to the energy the electron needed to lose to end up at a lower permissible level of energy. Remember conservation of energy here. In 1917, Rutherford did an experiment where the gamma rays were shown to reflect off a crystal surface in a way similar to X-rays. So he concluded that gamma rays were high energy electromagnetic radiation. To explain how these high energy photons were created, Ivanenko and Gabon suggested that the nucleus itself had an energy structure with discrete energy levels. A more sophisticated model was proposed in 1949 by Maria Goeppert-Mayer and Hans Jensen. The previous history leads to the gamma rays being high energy photons that are emitted when nuclei with more energy than their minimum level lose some energy to reach another acceptable energy level. When a nucleus is in a configuration with the lowest energy, it is said to be in the ground state. Otherwise, it is said to be in an excited state and identify as such with a star. A gamma decay involves the emission of a high energy photon when an excited nucleus loses some energy to reach an acceptable level. We start with an excited parent nucleus. This parent nucleus could be the daughter nucleus of an alpha or beta decay that was left with more energy than its ground state. That excited nucleus loses energy and very often goes to a ground state and emits a photon in the gamma range. Note that the subscript and superscript indicate that the photon has no charge and is not a baryon. As an example, I will use the excited protactinium-234 that was a result of a beta-negative decay in a previous example, and let it go to its ground state and let it emit a gamma particle.
So far, our study of radioactivity did not involve much quantitative assessments of the physical situations. It is not possible to predict in advance when a particular nucleus will decay. However, the behavior of a large number of them follow a characteristic that can be quantified. This will be the subject of the next installment.